Hmm. So in the last episode, we have discussed it till 19th question. So we will start with the 20th question. So in this question, they had given that primary is delta and secondary is star. Okay. So and they had given that phase turns ratio of secondary to primary. So V delta phase by V V star phase by V delta phase is equal to 6. Okay. So this is turns ratio which is equal to voltage, right, in general. So this is given. Okay. So they had given that primary voltage is 200 volt. Okay. The primary voltage is 200 volt. In general, if in question it is not mentioned that phase, or in question if it is not mentioned phase, we always take it as RMS voltage. Okay. So given 200 volt is RMS voltage and it is a primary. Primary is what? Delta. So in delta, phase voltage and line voltage are equal, right? V line and V phase are equal. So if you put here, so V star phase by 200 equal to 6. So V star phase equal to 1200. Okay. So they ask the secondary voltage. So they haven't mentioned the phase term. So we should express in RMS. Okay. So V star line voltage equal to root 3 into phase voltage 1200. Okay. So it will result to 27.8 volts. Okay. So no need to calculate this because see in the options only the voltage which is greater than 1200 is option A. So directly you can answer that. Okay. Okay. So coming to the next question 21. So the iron loss is given 1 kilowatt and copper loss is given as 2 kilowatt. Okay. So they ask the maximum efficiency occurs at which load. Okay. So we know that the kVA rating at maximum efficiency, okay, is equal to the full load kVA into root over P iron loss by P copper loss. So full load efficiency they given, sorry, full load rating they are given 100 into root over iron loss is given as 1 kilowatt and copper loss is 1 by 2. So 100 by root 2, which is equal to 70.7 kVA. So answer will be B. Okay. Coming to next question. So this is a lap wound DC generator. In lap wound generator, generally number of parallel paths equal to number of poles. Okay. So we know that generated EMF formula equal to Zn P5 by 60 into A, right? So P and A will be cancelled because those are equal. So Z number of conductors. If you see the number of conductors is given as 250 and the speed is given as 1200 rpm. The flux, uh, they ask the flux only, and by 60 equal to the EMF is 200. Okay. So 600 if you multiply that side, so 60 into 200 by 1200 into 250. So these two will cancel, and so 1 by 25 will remain. So which is equal to 0.04 Weber. Okay. So answer will be B. Okay. So coming to 23 question, the highest speed attainable by the DC shunt motor. Okay. Generally, this is the DC shunt machine. Okay. And the voltage is V. If you write the expression, so V equal to E plus IARA, right? So E equal to Ka phi into omega. So if I write it, Ka phi into omega plus IARA equal to V. So I want to write omega equal to V minus IARA by Ka into phi, right? So omega equal to V by Ka phi minus IARA by Ka phi, right? So during the no load, the armature current will be 0. So the speed is V by KFI. Okay. Now, during load condition, when load condition, IA will be finite. So IA will be finite. So omega equal to V by KFI minus some finite value. So the speed will be less than the VA KFI. So speed will be decreased, right? So the highest speed is achieved during the no load only. So it is equal to no load speed. Okay. Coming to 24. So the direction of the rotation of DC shunt motor can be reversed. Okay. Let me take a DC shunt motor, and this is the supply. So we want to rotate, change the direction of the shunt motor. Okay. So in general, the electromagnetic torque and speed will be same direction, and the prime mover torque will be in opposite direction. This is for motor case, right? This we know. So in order to make this rotation, I mean the electromagnetic torque supports the speed. Okay. So in order to change the speed of the DC motor, we will change the torque. Okay. So torque we know is proportional to phi into Ia. So change the flux only or change the armature current only. So like if it is minus, it should be plus. If it is plus, it should be minus. Then only electromagnetic torque will be negative, right? So if both will be negative, the electromagnetic torque will be positive. So the direction will not be changed. So either you change the flux value or either you change the armature current value. Okay. So what I will do, so this is the flux. So in general, armature current it is, and it is field current, right? And this is supply current. And this is positive and this is negative. So the same thing, this is the motor, right? So what I will do, so I will connect this terminal to here, and I will connect this terminal to here. So the current start flowing like this, and it will go like this, and it will go like this, right? So initially current is coming from top to bottom, if you observe here. So now current is going down to top. So current is reversed. So IA is reversed. So IA will be negative, suppose. Now IF, if you see IF, it is same as the above condition, right? So IF is responsible for the flux, right? So it will be positive. So by changing the armature terminals, okay, so we can reverse the electromagnetic torque, so we can reverse the speed, right? Now I will do one more thing. So I will take the motor, supply will be same, but I will change the field terminals like this, okay? So armature current will be like the first case, but the field, if you see, the current like come here and it will go like this, right? Now in this case, IF is negative. It means flux will be changed, but the armature current is same as the first condition. It will be positive. So in this case also, electromagnetic torque will be negative and speed will be changed. So there are two cases that you can change the armature terminals also. You can change the field terminals also. So both options are correct. So either field or armature terminals. So this answer is the right. So here the term only, you know, so it is wrong. So it is wrong. Only because of that only it is wrong. Okay. Okay. So coming to 25th question. The poles of the DC machines are laminated to reduce what? Okay. So this is a pole, right? In general, we will give supply to here. This is DC supply. So the flux will be constant in nature. Okay. If the flux is constant, okay, the eddy current, oh sorry, the eddy EMF will be zero. because in order to produce the eddy EMF, okay, so we need the flux will be time variant. So flux should be time variant. Then only eddy EMF will induce. But here, due to the field flux, there will be no eddy EMF will be induced, so that there is no eddy current. But if you see in the armature, okay, due to the armature, we know that in armature, AC flux will produce, right? After, by commutator, we will get DC output, but in general, in the armature, AC flux will develop. So this links with the pole shoe, okay, this links with the pole shoe, and it will induce an eddy EMF. Okay, this EMF, eddy EMF, results to eddy current. So this will results to eddy current loss. Okay, so in order to reduce this eddy current loss, in general, poles will be laminated. Okay, poles will be laminated. So answer will be A. Okay, okay. Hmm. So coming to 26th question, let me tell you the braking system. Okay, so let me assume a DC shunt machine. Okay, this is the supply voltage. Okay, so what the conditions are? Suppose this is the motor. If you change the supply terminal like this, okay, okay. So this case is regarding to plugging. Okay, and the second condition is disconnect from the supply the only armature. Armature will be disconnected from the supply and a resistance is connected across the okay motor. So this will motor current will reverse. So this condition is called dynamic braking. Okay, dynamic braking. So in general, regenerative braking will happens when the EMF back is greater than the supply voltage. Okay. So if you observe this, the supply polarity to the armature terminals is reversed. Okay. Supply polarity means this one. Okay. So this condition is reversed to plugging. Okay. So coming to 27th question. So for the welding purpose, the secondary of the transformer. Okay. Now let me tell you, for the welding purpose, we generally use step down transformer. Okay. Step down means low voltage and high current. So high current. Okay. So why we use the step down means suppose these two are the no uh, things we need to weld. Okay. So we use electrode to fill this right to fill this gap and to weld this two metals. Okay. So we require high current to produce the sufficient heat. Okay. To produce the sufficient heat, like you will need more heat required to melt that. So why low voltage is required is if low voltage is responsible for the arc length. Okay, so if low voltage is there, the arc length will be less. So the arc will be confined to a particular region. So where the metal should be welded. So that's why the low voltage is needed. Okay, so the answer will be low voltage and high current. Okay, okay. So coming to 28th question, let me explain you. 28th question. They had given that frequency is increasing and voltage they are maintaining constant. Okay, so what will happen to hysteresis and eddy current loss? So generally we know hysteresis loss is equal to proportional to P max 1 power 6 into F, and eddy current is loss proportional to B max square into F square. So which is proportional to V power 1.6 by F power 1.6 into F, and proportional to V square by F square into F square. F square will be cancelled. So hysteresis loss is proportional to V power 1.6 into F power or V by F power 0.6. The eddy current loss is proportional to V square. So eddy current loss is independent of the frequency. So if frequency also increased, eddy current loss will not affect it. Okay. Coming to hysteresis loss, frequency is increasing. So hysteresis loss will be decreasing because those two are inversely proportional to each other. So hysteresis loss will be decreased and eddy current loss will increase. So here this answer is wrong. Actually, D is the right answer. Okay. So you understood that. So I written B max is proportional to V by F. So I have written this. Okay. So there is a transformer given. High voltage and low voltage transformer is given. It is of 1100 by 220 volt. Okay. So high voltage resistance is given as 0.10 ohm. So low voltage resistance is given as 0.004 ohm. Okay. So the equivalent resistance referred to high voltage side they ask. Okay. So if this is referred to here, so it will be so 0.1 plus 0.004 by k square. So at k equal to N2 by N1, which is equal to V2 by V1. So which is equal to 220 by 1100. So it will be, so k will be 0.2. Okay. So which is equal to 1 by 5, right? So 0.1 plus 0.004 by 1 by 5 square. So which is equal to 25. So 0.1 plus 0.004 into 25. So which is, this is equal to 0.1. So it is, when it is referred to high voltage side, answer will be 0.2. So the only option will be this one. Now when it referred to low voltage side, so answer will be 0.004 plus 0.1 into k square. Okay. The k value will be the same, this one. Okay. So if you substitute this, you will get 0.08. Okay. Coming to question number 30. So the commutator in DC machine acts as, okay. In general, in DC generator, usually AC to DC, right? Commutator action. Okay. This is commutator action. Okay. In case of motor, DC to AC. This is the action of the commutator. So here they said that mission. So it will be AC to DC. What will it do? Rectifier, right? So DC to AC, inverter. So they haven't mentioned whether it is generator or motor. So we will go with the rectifier and inverter. So both A and B, either A and B. Okay. Okay. So coming to question number 31. So the purpose of the dummy coil. Okay, let me tell you what is dummy coil. Okay. So generally this is a mission and there will be slots like this, right? So okay. So in general, what we will do, the coil will be placed here, right? The coils will be placed in the slots, right? Okay. So, but in particular, in wave winding, during the design process, there may be a chance that slots will be empty. Slots will be empty. Okay. So if you see this, this is copper. So this slot has more weight and this slot has a more weight, but there is no coil inside this slot. So this weight will be less, right? So when the machine is rotating, there is non-uniformity is there because of the at some portions the weight will be there and some portions the weight is not there. So due to this, the machine may get vibrated. Okay. So what we will do, we will place a dummy coil. Okay, we will place a dummy coil so that the uniformity will be maintained and the machine will rotate smoothly. So, uh, so the purpose of dummy coil is to provide the mechanical balance. Okay, to provide the mechanical balance. Okay, so answer will be C. Okay, okay. Coming to, okay. Coming to question number 32. So the number of brushes required for a DC machines with wave winding. So in general, number of parallel paths equal to number of brushes. Okay. So in case of wave winding, it is fixed. So number of parallel paths equal to 2. So the number of brushes will also equal to 2. Okay. Question number 33. So the function of interpole. Okay. So in general, interpole windings are also called commutator poles, commutating poles, or we can call as commutating poles. Okay. Why? Because so what we will do is by introducing the interpole winding, we create a dynamically induced EMF. Okay. Dynamically induced EMF. So during the commutation process, if we study, there is a voltage called reactance voltage. Okay. Okay, this will produce. So by introducing of interpoles, we create a dynamical induced EMF. It will neutralize this reactance voltage. Okay, this reactance voltage and improve the commutation process. Okay, so that's why interpoles are also called commutating poles. So the function of interpoles in DC machine is to provide the commutation. Okay. Hmm. Okay. So the commutator segments of a DC machine are made up of. This is direct bit. So there is no explanation is needed, I think. So the commutator segments are made up of hard drawn copper. Okay. Brushes, carbon brushes in general. We use the carbon brush. Okay. Hmm. Now coming to 35th question. Okay. Which of the following transformers secondary is always kept closed? Which means secondary winding should not be open, right? So if you see the current transformer, CT, so there is a bar primary and there is a secondary. Okay. And it is shorted with some ammeter. Okay. So why it should not keep secondaries open? Let me explain you. So in general, the primary will produce an MMF. Okay, N1 N into I1. So in general, in transformers, we know that the secondary flux will oppose the primary flux, right? Now suppose in secondary, if you keep kept open, okay, the secondary current will be zero and the secondary flux will be zero, right? So the only MMF is the primary MMF, which is large, right? Because in CTs we generally connect with the line current, so which is very large. So that's why the flux is also large. So there may be chance that it will go to saturation. Okay, it will goes to saturation. And second reason, this large flux. Okay, this large flux links with the secondary winding. Okay, so there will be EMF will be induced. So this EMF will be large because of this large flux. So this EMF will damage the insulation of the secondary. Okay, so because of these reasons, we should never open the secondary of the CT. Okay, so answer will be the current transformer. So coming to 36th question. So they asked the inductive power transfer. So in general, the inductive power transfer is equal to 1 minus K of the total power transfer. So where K is LV by HU. If you see in the question, they mentioned that V2 is less and V1 is greater than. So LV will be V2 and HV will be V1. So inductive power transfer is 1 minus V2 by V1 into ST. So they asked the fraction. So this they ask. So V1 minus V2 by V1. So option will be D. Okay. So coming to 37th question. So stepped core use usual transformers in order to reduce what? So generally, if you see the transformer, it is generally made up of so many sheets like this. Okay. In this, we generally place the winding, right? I mean, so winding will be like this. Okay. So if draw this portion only separately, so the core is like the shape. Okay. So the winding is like around this core, right? Now if you see this, now what I will do is I will make a step. Okay, like this. Now I will wind the core around this. Okay. Now if you compare first and second case, the circumference of this first one is high compared to the circumference of this second one. So if the circumference is more, so the winding which required is more, right? So by using the stepped core, the circumference will be less, and the volume of the copper requirement will be less. Okay, so option will be B. Okay, coming to 38th question. So they given that EMF induced in the DC generator is 230. So E equal to given 230, and armature resistance is zero point 0.1. So armature current is 200 amperes. So the terminal voltage is simple direct bit V equal to E plus IARA. Okay. Hmm. Sorry, this is in the case of motor, but here they are given for generator, right? So generator E equal to V plus IARA. So they ask the voltage V. So V equal to E minus IARA. So E equal to 230 minus 200 into zero point 0.1. So which is equal to 210 volt. So answer will be B. Okay. Hmm. Now coming to 39th question. The commutator of the DC generator is acts as, we already discussed. So DC machine, the commutator acts as a rectifier and inverter. But in case of generator, so in generator it acts as a rectifier. Okay. The transformer used in the welding set. This already we discussed. We need high current and low voltage. So this can be attained by step down transformer. Okay. So answer will be B. Okay. Coming to question number 41. Okay. So an AC supply of 230 volt is applied to half-wave rectifier through a transformer of turns ratio 10:1. Determine the peak voltage of across the diode. Okay. So the peak inverse voltage. The peak inverse voltage will be Vm. Okay. So now come to what is V here. Okay. So here this is 230 volt and here 10:1 transformer is there. So the voltage across here is 23, right? So this is the RMS voltage, right? So RMS voltage we got 23. So peak voltage, PM is a maximum peak voltage, right? So peak voltage equal to 23 root 2. So 23 root 2. We have to get 23 into 1.414. Okay. So if we calculate this, it will be around 28 plus. So we can write 20 plus 3 into 1.4. Let it be. So it will be 28 plus 3 4 12, 4.2. So 32.2 something, right? So most probable answer is option B. Okay. Now come to 42. So if you see the 42, they had given delta to star phase to phase. So means V delta phase by V star phase equal to A by 1. Okay. The line to line voltage transformer. So in delta, line and phase are equal. So in star, VL equal to line voltage is 3 times of phase voltage. So I can write V delta phase is equal to V line by root 3, right? So I substituted here equal to A by 1. So they asked line to line voltage of star to delta. So V star line by V delta line equal to root 3 by A. So you just adjust the numerator and denominator. then you will get root 3 by A. So answer will be option D. Okay. Now come to 43rd question. Which of the following motors can run on AC as well as DC? As well as DC, both AC and DC. So out of the four options, only the universal motor which run on AC plus DC. Remaining all three will be run on only AC. Okay. So this is also direct, bit. So come to 44. Okay. So a 10 watt. So this is correction. This is not 10 watt. This is ohm. So a 10 ohm resistive load is to be impedance matched with a source of 6250. Like this is 6250 and there is a transformer is there. Okay. So and there is a 10 ohm resistor is there. Okay. So impedance matching is happening. Okay. This is 6250. So N1 is to N2. Okay. If you transfer this here, 6250 and this is 10 by k square. So where k equal to N2 by N1. Okay. So for the impedance matching, these two will be equal, right? So 6250 equal to 10 by k square. Okay. So they ask for the primary to secondary. So they ask for 1 by k. So what I can write is 1 by k square equal to 625. So 1 by k equal to 25, right? So they ask for 1 by k value. Because if you see primary to secondary they ask, but we expressed k is N2 by N1. So answer will be A. Okay. Okay. So coming to 45th question. Two DC series motor are connected in series to draw a current. So there is one motor and other motor. These two are DC series motor connected across a voltage V. So these two are similar. So V by 2 and V by 2. So current is I. Now what happened? Same two motors is connected in parallel. Okay. Now V. Okay. And supply current is I. So here I by 2 and here I by 2. Okay. So in general, we know that E1. So this is E1 and this is E2. Okay. The first case, in the first case, this is the first case and this is the second case. So in first case, E1 equal to what we can write V by 2 minus I into RA, right? So what I will do, I neglect this drop. This is approximately equal to 0. So E1 is proportional to V by 2. Okay. Now come to second case. Second case, so E1 is equal to V minus I by 2 into RA, right? So generally I consider resistance of the armature resistance is very less. So I will again consider this drop is 0. So here E1 is proportional to V, right? So we know E is proportional to N into 5. So I will represent E1 dash here. So E1 by E1 dash equal to N by N dash into 5 by 5 dash. Okay. So E1 is proportional to V by 2 divided by V equal to N by N dash. So here phi is proportional to I, right, armature current, because here it is DC series motor. So in the first case, phi is directly proportional to I. In the second case, phi is directly proportional to I by 2, right? So I by 2. So 1 by 2 equal to N by N dash into 2. So N dash equal to 4 times of the N. So answer will be 4N. Okay. Thank you.